We're going to start with an example right out of yesterday that I find to be, it's exactly the same as yesterday, but it's going to allow me to introduce something else. So, yesterday we had like a 6 kilogram box, a 5 kilogram box, and that was it, right? It was a 2 kilogram box? All right. Well, I'm going to change it all up today. So, here we go. Not much. I'm going to add a box. So, this one's 6 kilograms, this one's 2 kilograms, and this one is 5 kilograms. You guys see that okay? They are connected together by a ideal rope. And on one side we're pulling with 10 newtons, and let's assume the coefficient of friction is 0 here. I would like you to find the tension in both cables between the boxes. That's the question mark. So for this problem, that's what we're looking to find. Okay? Now, I'm going to do an aside. Do you know what an aside is? I want to talk to you about something that's not about the main topic, but is related to the main topic. Can I do that for a second? So here's my aside. We're going to deal with mostly ideal situations. And an ideal situation often includes things that aren't the way the real world works. Ropes, cables, that's one of them. Almost all of our examples are going to be ideal ropes, ideal cables, or ideal strings. And to be careful here, I want you to be aware that in AP Physics 1, that's all we ever talked about. But in this class, we will often, or at least a little bit, talk about the difference between ideal and real, and some of your problems could involve real ropes, real cables, real strings. The biggest difference between the two, real ropes, real cables, real strings have inertia. They have mass. And because they have mass, they are a part of your problem, right? They add inertia to the system. And because they add inertia to the system, they change the behavior of the system. So adding a rope instead of just pushing two boxes together and putting a rope between them actually changes the system because the rope has inertia. Repeat that like 3 times. Real ropes, real cables, real strings, they have inertia. Ideal cables don't. And because of that, ideal cables don't sag because they're not affected by gravity. They don't stretch. And the most important thing about real cables versus ideal cables is real cables have the same tension throughout their length. So if you apply tension to a cable, whatever tension you apply to an ideal cable will be the same everywhere. Did I switch that? Okay, let me be very clear. Ideal cables have the same tension throughout their length. They don't stretch, they don't have inertia, and they have the same tension throughout their length. So if I reversed that a minute ago, strike it in your notes and fix it. Real cables stretch. Real cables don't have the same tension throughout their length. In fact, let's do a quick example of something, and I think you'll get it right away. Let's hang a cable from the ceiling. So this is a real cable hung from the ceiling, and let's say it's a thick enough cable where it's a total mass of 2 kilograms. And more than that, let's say it has uniform mass density. How many of you know what mass density is? It should be 100% of you because you made it through chemistry. And chemistry deals with density. And density is a physical attribute. It's mass over volume. And some of you are in orchestra. And you understand that stringed instruments have different mass densities for the strings. We would call those linear mass densities. So the thicker strings play the lower notes and the thinner strings play the higher notes. You're buying your cables based on their linear mass density. You don't know it that way because that's not how they're sold. They're sold by the key of the particular cable, but that's not what they are. They're based on their linear mass density. So they have uniform linear mass density, which means they are the same mass density throughout the length of the cable. Does that sound like the strings of your orchestra stuff? So, if you hang one of these strings, is it clear that at the point where it's hung, right up here at the top, that whatever it's mounted to would experience or have to apply 20 newtons of upward force to keep the cable from falling, because it's a 20 Newton cable. How much force do you think there would be for the last little bit of cable? Like if you consider that each piece of cable is holding the piece underneath it, all the way at the bottom, the last little piece probably doesn't have to apply any force, right? Like, what do you think here? This part of the cable has to hold all of that, right? So there's a tension in the cable because it has to hold the cable portion that's beneath it. So the tension here is probably greater than the tension here because our cable has mass. So this part of the cable holds all of this, while this part of the cable only holds that much. Do you see why the tension would go up as you went towards the top of the cable? That's what a real cable does. Our cables are ideal. They don't have mass, so this doesn't happen. But real cables have mass. Now, to give you an example of how that might be used, and this is not an example I'm making up, this is an example that was actually on the AP exam. Imagine a table in the middle of nowhere. We take that same 2 kilogram cable, but we place it here at the edge of the table. Right? If you were to grab the cable here and pull this way, is it clear to you that the more cable that makes it onto the table, the less force you have to apply because there's less cable hanging off the edge? Does that make sense? Well, imagine the reverse of that. What if all the cable is on the table except for a little bit? If there's no friction on the cable, is it clear that there's a little bit hanging off, so there is a downward force on the cable? So the cable will accelerate off the table. Does that make sense? Is it also clear then that the more cable that makes it off the table, the more force there is on the whole cable? So the acceleration of this system increases over time. This is not a constant force. It's an increasing force, and it's a force that increases the acceleration, so the acceleration is always changing. So if I asked you to figure out how fast the cable's going when it's all off the table, you would have an acceleration that was constantly changing. That would be a complicated question involving calculus. And that's because this is not an ideal cable. It's a real cable. This was on the AP exam a couple years ago. So it's not out of the question that you might be asked things like this. And so we need to be prepared for that. Now, we're not going to do this problem right now. We're going to do this easy one right now. This is the one we're going to do. And like I said, we're going to treat all of our problems for this particular unit as having an ideal cable or an ideal string. We'll get to the non-ideal ones, the real ones, later. So take a second. I'll give you a few moments. How about we start with where we started yesterday, free body diagram? Seem reasonable? I'm going to label these for you. I want this to be called T1 and this one to be called T2. And eventually I want you to tell me what T1 and T2 are, or at least be in a position to do so. So let's go. Give it a shot. See what you can do. We did this problem yesterday with 2 boxes. Okay, I'm going to pull us back together after I answer this question. Being able to exploit a student for fun, but this is not exploitation, okay? So since I'm recording this, I won't say the student's name, but I will say that there is a reason why you might make a free body diagram for the rope. If the rope has mass, you would have to draw a free body diagram for the rope. That's the whole point of the conversation about the difference between ideal and real. Ideal ones having no mass means they have no inertia. So we don't have to draw a free body diagram for them, which is, in this case, what we're doing, which is why it was silly that you were drawing a free body diagram for the rope. But in a situation in which the rope has mass, you would have to treat it as another box. So that's not out of the question. But we're not doing that, like I said at the beginning of this. We're just drawing free body diagrams for the boxes. So let's do that. Now, I've been careful to color code everything, but for this particular example, do the weights and normal forces matter in this problem? Like the net force in the y dimension is going to be 0. Would you agree? And there's no friction, so we don't have need of figuring out what the normal forces are. Does that make sense too? So I think we can focus on the horizontal forces for this one. But if you did draw the up and down forces, good on you, but you should start considering scale. So, I mean, for the first one, this would have to be 50 units long, while this one's only 10 units long. You see what I mean by scale? That might become a problem. So I'm just going to leave out the up and down forces for right now and focus on the side-to-side forces. But I do want to consider scale. Do we think all these boxes are going to accelerate? I think so. There's an unbalanced force acting on a system with no friction. I think the system's going to accelerate. Do we all agree that it's probably going to accelerate to the right? Okay, with that being said, the 5 kilogram box must be experiencing an unbalanced force. So when I draw my 10 Newton force to the right, I'm going to draw my T1 force to the left, but intentionally make it smaller to demonstrate that it's accelerating to the right. But I know because of Newton's third law that the tension on the green box, which is one of them is to the right, has got to be the same size arrow, because that's my Newton's third law force. But there's another tension on the green box, which is to the left. Again, I know it has to be smaller because the forces on the green box have to be unbalanced for it to accelerate. Leaving me with the red box, which only has one horizontal force, T2, and it is to the right. And that should be the same size as T2 to the left on the green box. Now I'm just color coordinating these to try and make sure they look separate, but I'm not going to stick with that all for the whole time, just for right now. Now that I've done that, unless the strings stretch, and we already indicated that they're ideal, right? That means that we can probably assume all three boxes have the same acceleration. Is that reasonable too? All right, so if they all have the same acceleration and that acceleration is to that direction, I think we can go ahead and build out a net force equation. And let's do that. In the interest of time, you should put it together. So let's be speedy. This should be like 30 seconds. That doesn't mean there's a whole lot to write. How about if I do this one, let's say 10 minus T1 equals 5A. Did you write that out? Does that make sense? Net force on the one block. How about T1 minus T2 equals 2A? Is that good? Make sense? Nothing bizarre here? I see you making changes, so I have to assume that either you didn't do it this way or you didn't do it at all. T2 equals 6A? All right. 3 equations and 3 unknowns. You see it that way? Whatever number of objects you're going to have, that many equations. You can have up to 6, really, if we include the net force in the y direction. Right? 2 equations for each of your objects. Plus, you throw in friction, there might even be more. If there's friction on each one of these boxes, we have as many as 9 equations for all 3 of them, right? 3 per box. You understand, this can probably get complicated pretty quickly. Change that rope out for some springs between them. Oh, yeah. I see some stuff in our future. Let's just handle this one, though. I said I wanted the tensions, but I think these problems are almost always better served finding the acceleration first. And there are some shortcuts, and we're going to talk about this shortcut in just a minute. But let's take a look at the 3 relationships that you should have generated. If I take these and put them together, is it pretty clear that if we add these together, the t's are all going to cancel out? You do understand you can add equations together, correct? You've done that before? The t's are internal forces. When we do this, we should be left with only external forces and the inertia of our system. So for every positive internal force, there should be a negative internal force. So I see a positive T1 and a negative T1, a positive T2 and a negative T2. Do you guys see all of those? So when I add them all up, I'm going to be left with 10. 10 newtons, the external force on the system. I'm also going to be left with 5 plus 2 plus 6. every time you do one of these, you should be able to get a net force on the system is equal to the inertia of the system times the acceleration of the system. Every time you do this, you should see at some point in your problem you adding up all of the masses. Every time. So if you do this problem, you never see the sum of all the masses, you're doing it wrong. There's a mistake. Now, just walk back with me for just a minute. This is a shortcut, and I want you to think about it. Does the 10 Newton force know that there's 3 boxes? No. What this shows us is that the 10 Newton force just thinks it's pulling on one big box. Right? If I treated the problem like this, it would have a mass of 5 plus 2 plus 6. Right? You could consider the problem as a system. In fact, we're going to talk about the difference between a system and individual objects. This is what the force sees when it's pulling on the box. That was proven right here. Right? So you can get to the acceleration of the system, but be careful when you do this. This works, but there are other external forces like friction and perhaps normal forces when you have a ramp and stuff. Be careful about how you treat the box like a system, but you can almost always treat it like a system. Almost always. Now, this works because every part of our system is having the same acceleration. That's why it works this way. But again, you're just going to get A equals 10 over 13 meters per second squared. If you want one of the tensions, which we're not going to do, you just take it and plug it back in here. Right? That'll get you one of the tensions. All right, let's try another one. Do a bunch of these. So let's go back to just 2 boxes, these 2. The 5 and the 6 connected together by a cable. Not a real one. Okay, just a perfect cable, an ideal cable. And let's pull with another cable on the 5 kilogram box upwards at 20 newtons. Now this one, I don't want to help you. I think I've given you enough information. I think I've given you a position to do these on your own. So I want you to tell me the tension between the 2 boxes. And I am not actively trying to trick you, but you might be tricked if you're not careful. So give it a shot. I want the tension between the 2 boxes. So free body diagram like this. Is that what yours looks like? I hope so. If it's not, what's wrong with yours? Let's fix it. I see 2 forces acting downwards on the 5 kilogram box and 1 force acting upwards on the 5 kilogram box. And I see 1 force acting upwards on the 6 kilogram box and 1 force acting downwards on the 6 kilogram box. Is that what you did? If you made a mistake, let's fix it. Did you make downwards positive? I'd make downwards positive. We know it's accelerating downwards, so I'd make downwards positive. You don't have to, but I'm going to. So when I work the problem, that's what I'm going to do. In fact, I'm going to say for this one, 60 minus t equals 6a. Is that what you're going to do? Is that what you did? I hope so. For the red one, 50 plus t minus 20 equals 5a. Is that what you did? That's what I did. I think that's a good way to go. Just adding up what's there. Add these together, and I'm noticing I'll have 50 plus 60 minus 20 equals 5 plus 6 times A. All 3 external forces, right? The 2 weights plus the upwards pulling force, and then the entire inertia of the system, and then the acceleration. Do you guys see all those pieces? Is that what we expect? 50 and 60 is 110 minus 20 is 90. So 90 equals 11a, so a equals like 8 meters per second squared downwards. Any question? I'm going to plug that back in, say here, to figure out what t is. That's how you get your 11 newtons. Another one? Let's bring back our two favorite boxes because they've been serving us so well. But this time, let's not leave out friction. Friction's been wanting to play for a while, so let's put our friction in there. We'll come back to our 10 newtons like we had before. Our 5 kilogram box, our 6 kilogram box. If I was to ask the question here, I would say, okay, we're pulling on this system to the right with a 10 Newton force, and we have broken static friction. So there's a kinetic friction of 0.2 between the boxes and the ground. I don't know whether the system is speeding up or slowing down, but I'd like the tension in the cable. So again, we've broken static friction, given the system some velocity. I don't know whether it's speeding up or slowing down. You should probably figure that out. But I like the tension in the cable. And you've got like 2 minutes for this, so you may not finish. I'll put the answer up there, and I will finish the problem and post it, but you should probably give it a shot. This is a good one. If you're trying to work this at home, I believe the tension between the cables is 5.4 newtons. You get an acceleration of this system that's like -1 meter per second squared with some change. Try it out, please. All right. So let's finish up.